Can you see my Canvas web page? Can everybody hear me?
Yes, we can see and we can hear you.
Okay, good. I am going to tell you that the test 1 is going to be on September 14. Okay. If you go to the calendar, I have changed it. So we're going to have a review on September 12th. So I'm going to finish chapter 2. We have a review on next week, Tuesday. All right. So if you check on the calendar, you will see that change. It's kind of slow. Right here, I change it to September 14. We're going to have a review on September 12th. All right. I'm going to, do you have any questions? Do you have any questions about the test date and anything else? Can you guys hear me?
Yes. No, we don't have any questions.
Okay. All right. I'm going to go to slides page. Can you see my slide page?
We can
Yes.
see.
Okay. Last time what we did was, let me go review a little bit. The test is going to be on September 14. I told you about that. We look into these topics: classification of matter, Dalton atomic theory, composition of atoms in terms of subatomic particles. We look into periodic table, classification of elements, nonmetals, metals, metalloids, and their properties. We started on electronic arrangement of electrons around the nucleus of atom. So last two sections, section 2.6 and 2.71, I'm going to cover today. So I'm going to start where I left off. Let me summarize a little bit. Electronic configuration of atom, how you get it. Let me go and electronic configuration is the arrangement of electrons around the nucleus. We already talked about nucleus. It's made out of neutrons and protons that has the positive charge, and most of the mass in the nucleus. The energies in the atom, electronic energies around the atom is quantized. What do you mean by quantized? They are discrete energy. Energy is like a ladder. So energy is these steps. Energy is not in between. That's why quantization means. So these energy levels are quantized. The ground state is the lowest energy level. Electrons normally go into the bottom level energy states in the atom. We're going to look at possible energy states available in an atom. electrons are waves. They are not particles. There are electronic shapes, which we call orbitals. They have a definite shape. One of the shapes that electrons take up around the atom is S shape. It's called S orbitals. These two. Now, p orbitals are little higher energy than s orbitals. They are dumbbell shaped. There are three of them in here: x, y, c, px, py. There are three p orbitals. I'm going to show them in a minute. Apart from s and p, we have d shapes and f shapes. That's the p shapes. Px, p, that's the s. That's px, py, pc shape. This is the d energy level. We are not going to discuss them too much. That's d. There are 5 of them. There are 3 p's, 5 d's, and 7 f shapes. Now, all the energy levels associated take up one of these shapes. Electron can pick up one of these energy levels. They are quantized. So we are going to look into how we assign them in a particular atom of an element. Electrons have spins. We're going to talk about spins. One of the s orbitals can pick up 2 electrons. They are anti-parallel. When they take up orbitals, they have anti-parallel spins. Orbital, when 2 electrons go there, they have different spins. We're going to talk about this. Now, these shapes are tied up to the periodic table. That's group 1A, 2A, or group 1 and 2. These are S block. It's called S block. This blue block is called transition metals. They are last electron added to them go to a D block. And this block is called P block. So lanthanide and actinide, which we put outside this is long form of periodic table. 2 rows, we said lanthanide, actinide. They are in F. They are called F blocks. Normally, electrons are filled into atom in this order. You start with 1s, then you start with 2s, right here. Then go to 2p. Then go to 3s and go to 3p, going across the period. So if you know number of electrons in an atom, you can start filling in this order. This order is given in the periodic table. So it's easy to get orbital electronic configuration from the periodic table. Normally, you get a periodic table like this. There are 2 areas, main table and two blocks called S blocks, lanthanide and actinide. These are the blocks called F block. These S blocks are in here. D blocks are in here. And the P blocks are in here. So therefore, if you are to get an electronic configuration, in the next, we're going to follow this order. If an atom has 2 electrons, it goes to 1s2. That's helium. Then if you have one more electron in 1s level, it goes to 2s1. 2s1 is lithium. That's lithium. So you can go through the number of electrons and using the periodic table, get the energy level, orbital energy level diagram, electronic configuration for any atom in the periodic table, following that order. Now, in the periodic table, the periods are called shell. There are up to 7, 5, 6, 7 shells. Shell number is called N number. N is equal to 4 here. So number of electrons that a shell can accommodate is 2n squared. That get, if this is 1 times 1, 2, 1 times 2 is 2. That's also 2 plus 2 squared is 8. That's 2 times 3 squared is 18. There are also, these numbers are also the number of elements that they have in the period. So that becomes 32. So as the number of shell number increase, energy is increased. Therefore, this order here, first you start with first shell with 2 electrons, and then go to second shell, third shell, and following the periodic table, electrons are added first to the most low energy levels, then you go filling it up. The further a shell is from the nucleus, larger its volume becomes and more electrons it can hold. We gone over this last time. True. How many orbitals are there in the 4p shell? Subshells. Orbitals are also called subshells. S subshell, P subshell, D subshell, F subshell. How many orbitals are in the P? There are 3 of them. You remember we counted 3 p orbitals? Answer is C. How many orbitals are there in the D sublevel? 5. We're going to talk about, do problems about shells and subshell structure of atom. Which of the following set of numbers could be designated to principal energy levels or shells? What numbers we use in subshell? There are 7 periods, 7 subshells, 7 shells. Therefore, it has to be 1, 2, 3, 4, 5, 6, 7. So answer is shells are period numbers. Shell number is same as the energy of the shell increase from 1, 2, 3, 4, 5, 6. Answer is C. Which of the following sets of alphabet is used to designate subshells or orbitals? We already talked about orbitals. We said there are s orbitals, p orbitals, d orbitals, and f orbitals. So out of these choices, that's the correct answer. We go over S, P, D, F only, nothing else. How many electrons can be accommodated in the fourth shell of atom? Fourth shells is N is equal to 4, 2 and 4 is 32. How many orbitals are there in D subshell? P subshells has 3 orbitals. D subshells has 5. F has 7. Answer is B. How many in P subshell? When you're talking about subshells, they are similar regardless of where they are. It could be 2p, 3p. There's no 1p. First shell has only s orbitals. First shell has only s orbitals. P subshells, how many electrons P subshell can have? There are 3 P's. Each can accommodate 2 electrons. Therefore, P times 2 is 6. Each orbital can accommodate 2 electrons. Therefore, P subshell accommodates 6 electrons. Answer is B. How many electrons can accommodate in D sub level? There are 5 D orbitals. 5 times 2 is 10. Answer is C. How many electrons can be accommodated in a 2D sublevel? Now, if you look at the periodic table, first period has only S orbitals, second period has, if you go through the periodic table, SP. Third cell have S orbitals, P orbitals, D orbitals. Fourth and onward has S, P, D, F. Therefore, there's no D subshell in second shell. That's the shell number. Fifth one has SP, DF as well. You can go and check in the periodic table. There are no 2D orbitals. None. There are no 2D subshells. Answer is D. Which of the following types of orbitals can hold maximum of 10 electrons? P's can hold 6. S's hold 2. D's hold 10. F's hold 40. Twice the number of orbitals. Therefore, answer is 10. Answer should be D orbitals. 10 electrons are held by d orbitals. Answer is C. Do you have any questions? Are you guys there? Can you hear me?
Yes, I can hear you.
Okay.
Yes.
Okay. We go on over this, how to get the electronic configuration. You get the electronic configuration of lithium. How do you get lithium in the electronic configuration? Lithium is Li. You go to the lithium. Lithium is right here. Second shell. Lithium has atomic number 3. Atomic number 3 on the top of the lithium. Therefore, 3 electrons. The filling order is 1s2, 1s, 2s, 2p, 3s is given in the periodic table. 3p, 4s, 3d, etc. It's given here, right here. You follow periodic table and get the filling order. Okay, lithium has 3 electrons. First one goes to 1s2. Remaining goes to, that's the lithium. How do you get lithium, beryllium? Beryllium has 1 more electron, 4 electrons. So you added 1s2, 2s2. That's it. So how do you get boron? Boron has 1 more electron. That means 6, atomic number is 5. 5. So 5 electrons. It's in P1. That's P1, P2, P3, P4, P5, P6. How do you get carbon? Carbon has 6. Therefore, it's going to be 1 more electron than boron. 1s2, 2s2, 2p. It's, to get the electronic configuration is easy. Did you see that? All this talk about quantum mechanics, wave shape are not necessary. You can give the answer based on the periodic table and orbital blocks, S blocks, using S blocks, D blocks, P blocks, and F blocks. So this is the second period and up to here, all these elements, electronic configuration. Rest is the similar. For example, if you had a titanium here, you go through this row, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and this is D block, D2. There are 2 electrons in the 1, 2. So also we abbreviate electronic configuration based on the noble gas. The noble gas before titanium is that. So we say electronic configuration is same as argon up to that point. Then you have 4s2, 3d2. So this is cutting down your, for example, if you wanted to get the electronic configuration of yttrium, you go to krypton, 5s2, 4d1. That's 4d. D orbitals are 1 behind the shell number. That's how you get electronic configuration. So we talk about filling order of increasing energy based on the periodic table. this is mapped out in the periodic table. If you go through periodic table in previous figure, you start with first period is 1s orbitals. Second shell is 2s 2p. Third period has this and SPD. 4s is filled before 3d according to periodic table. 4s is filled. So you can, this is obtained from the periodic table itself, going through the periodic table in energy level diagram. Each orbital is 3p's, 5d's, 7f's, has 1 orbital, 3 orbital, 5 orbital, 7 orbital. Each orbital can hold up 2 electrons. Therefore, s orbitals can have maximum of 2 electrons. P can have 6 electrons. D electrons can have maximum of 10. F orbitals can have 14. We gone over there in previous problems. With 4 electrons in the 1s, and this is the electronic configuration of with 4 electrons. That's beryllium. Beryllium has atomic number. This is same as beryllium. When with additional 6 electron in the p subshell, p orbitals, they are described in detail. This is px, py, pc. Rather than 2p6, we write 2px, 2py, 2pc. Then 2 of them in each one make it. Okay. We can describe 3 sublevels of p orbitals in a way. For example, carbon has 1s2, 2s2, 2p2. If you break down 2p2, there's 2 electrons in the first 2 energy levels. Now, sometimes we write down in the to show the unpaired electrons, that's the px, pyc. The 2 electrons are distributed normally when you filling up energy levels. You add 1 electron with parallel spin until they are all parallel, then fill up with the parallel spin. If I have more electrons, I add it to them. We're going to talk about that in a minute. So therefore, electron configuration could be described in detail with this idea about s orbitals, p orbitals, d orbitals, f orbitals. In the region of periodic table associated with lanthanide and actinide, which orbitals, or which subshell is the lanthanide, which block is the lanthanide actinide block? Remember we said the bottom 2 rows in the periodic table are lanthanide, they are F block, 4F and 5F. If you go back and look at the periodic table, you can, they are F blocks. D. Electronic configuration in ground state. Ground state is like in a multi-story building. Ground state is the ground level. Then you have first one, second one. What we call ground state shell is number one. Ground state, lowest energy state is the first one. When electrons are filling an atom, they go to the lowest energy possible. That is 1s level. Then after 1s2, you go to 2s2. Then after filling 2p has 6, you go to next level in the filling order. What you get adding electrons to the lowest energy state is ground state. What is the name given for the lowest possible energy state of the electron? That's called the ground state. Which of the following represent the correct order of filling orbitals? This is the filling order. If you look at that, this is correct up to here. But you cannot fill up after 2s. You go to 2p. Therefore, this is not the correct one. 1s, 2s, 2p, 3s, 3p. After 3p, it's 4s. Therefore, not in the filling order. When you go through the periodic table, orbital blocks across the period, you get 4s. At 3p, after 3p is 4s. 1s, 2s, that 3d is not correct. After 2s, 2p is not correct either. 1s, 2s, 2p, 4s, 3d, etc. Okay. None of them are correct. Did you see that? None of them are correct. D is the correct answer. I need to change that. Which of the following has the following electronic configuration? Which one? I cannot see here. If you look at here, this is how many electrons? 2, 2, 4, 10, 30. 13 electrons. It's same as atomic number. Therefore, in the periodic table, the atomic number 13 is aluminum. This is the correct filling order of atom with 13 electrons. The element is aluminum. Electron can sometimes fill orbitals in a manner that they defy rules, filling order. If they do so, we say atom is in an excited state. Suppose you are supposed to fill up rooms in a multi-story building from ground state to higher up. If there's a vacant room and you put somebody in the 4th level, that's the excited state. Now you have to check that out, filling order. This is correct, this is correct, this is correct, this is correct. That's not an excited state. This is correct, this is correct, this is correct. This is an excited state. 3s has to be 2, not 1. This is correct. But this is not. End statement. Therefore, total end statement, true, false, become false. AND statement. We talked about it. If a truth statement connected by another false statement by AND statement is false. Neither no, that's this is correct. Therefore, it's not true. This is ground state. This is excited state. So therefore, no statement also not correct. So only clear statement that is excited state is B. Electron can sometimes fill orbitals in a manner that defy rules, filling order. If they do so, we say that the same question as which represent the excited which state of this answer to this question. This is not excited. This is normal state. This is normal state. This is excited state. So is this, because 2s has to be 2. So C should be the correct answer. Neither. Okay. We got rough idea about ground state and excited state from the electronic configuration. The filling order of energy orbitals, sets of S has only one orbital. P has 5. Each orbital becomes half filled before any of them become filled. If you have P3, you put 1 in here, 1 in here, 1 in here. Then after that, you fill it up with another electron. So if you have D5, you put 1 electron in each with parallel spins and start filling from this one when one more electron is added. For example, this is carbon. Carbon has 1s2, 1s2 here, 2s2. For S levels, this is not applicable. Sets of orbitals of equal energy. Set means 3, 5, 3, 5, 7. F orbitals have 7 equal energies there. So these 2 electrons are added up parallel before pairing it up. Therefore, electronic configuration, detailed electronic configuration of oxygen, carbon is this. This is the idea about box diagrams. To show electron orbital details of electron configuration. This is normal form. Then each orbital is represented by a box. So that's 2p2. 2p2 here. So this is carbon. So this is the idea that how you get the electronic configuration and show how the electrons are distributed in the atom outside the nucleus. This is nitrogen. This is nitrogen electronic configuration. This is the box diagram. You write down 3 boxes here. one box, 1s has only one orbital. Therefore, 1s2 is, when you're filling one orbital, you go with there are 3 p's. You put parallel spin, 3 of them. How many unpaired electrons? Now, if you look at this diagram, these are paired. These are paired. These are unpaired. Unpaired electrons are in here. So there are 3 unpaired electrons. B is the answer. Now I'm showing you how to get the electronic configuration and figure out the number of unpaired electrons. Ground state electronic configuration of oxygen is this, same diagram. Now 1s, 2 electrons, you go write down 1 here, then 4 electrons. You fill with parallel spin, then you add it to that one. Therefore, there are 6 paired electrons, 2 unpaired electrons. So therefore, it should be 2 unpaired electrons. Fluorine electronic configuration is this. We obtain from the periodic table. There are 2 paired electrons in each 2s level, then 5. That's how you feel. 5. You fill up with the parallel spin, then pair up. That's 1 unpaired electron. Therefore, answer should be 1. How many unpaired electrons is the boron atom with the electronic configuration? You do the same thing. There are paired electrons, 1 unpaired electron. Now, we're going to understand little more details about electronic configuration. I cannot see. Valence shell. Valence shell electron configuration. Valence shell is the outermost. How do you figure out valence shell is? For example, lithium is 1s2, 2s1. The highest shell number is called the valence shell. Electron in a valence shell. Valence shell is the outermost shell with the highest shell number. We're going to incomplete shell. Normally atoms have incomplete shell electrons in the valence shell. All others are filled up. We write down Lewis dot symbol. We write down, for example, carbon. Carbon has 4 valence electrons. 2 in the first shell. For example, carbon is 2s2, 2p2, 1s2, 1s2, 2p2, 2s2, 2p2, 6. The valence shell is here, highest shell number 2. This is not valence shell. Therefore, electronic configuration of carbon has how many electrons? 4 electrons. We're going to show how we write down valence electrons. In the group 1, where hydrogen, lithium, sodium, potassium group, It has only one electron, 1s1. Valence shell is 1s1. Lithium has 2s1. Sodium has 3s1. So in a chemical group, Lewis dot structure shows the number of valence electrons. This is useful in describing bonding later. That's why we talk about Lewis dot structure. Next chapter, we're going to use this idea. Second shell, right here, second period, 2a, 2 electrons. This is in S1, S2. Third period is S2, P1. This is S2, P1. This is S2, this is S1. Like that. One thing nice about this is third group. All the elements in the group has same Lewis dot structure. Carbon is, I showed you here, carbon is 4 electrons. This is P X1, PY1, PC is 0. There's nothing in the P0. Therefore, we don't write down. Fifth period, fifth group, this is the fourth group. It's nitrogen. This has S2P. Then another dot here, P3. Therefore, 3 unpaired electrons, like we described before. Even any element in the group has the same Lewis dot structure, Lewis dot symbol. Oxygen has 6 electrons, and 2 of them are in the 1s. 2s is 4 electrons, 4 electrons. This is the idea. Oxygen has 2 unpaired electrons. Sulfur also has 2 unpaired electrons. Fluorine has 1 unpaired electron. 7 valence electrons. 4 valence electrons. Five valence electrons, 4 valence electrons, 2 valence electrons, 3 valence electrons, 2, 1, 1, 2, 3, like that. The chlorine has 1 unpaired electrons, 1 unpaired electron. Helium, except helium, noble gases have all full shell. It's called an octet. Except helium. Except helium, all the noble gases have 8 electrons in the valence shell. So these are useful ideas later on. You have to know what is the valence shell. Is the highest, outermost, highest shell number in the atom in the ground state, or the outermost incomplete shell in the electronic configuration. This partly explains why chemical properties of elements in a group are similar. They have same valence electrons in the valence shell. For example, beryllium has 1s2. How many valence? Valence shell is 2s. There are 2 valence shell electrons, these 2. So number of valence shell electrons for the group 2 is same. Beryllium magnesium, calcium, etc. So chlorine, bromine, iodine all have 7 valence electrons. The valence shell for chlorine is third shell, N is equal to 3. You look at the highest number, shell number on each subshell. These are first shell, second shell, these are co-electrons. Valence shell is the outermost. Therefore, N is equal to 3 for the valence shell number. There are 7 electrons in chlorine, bromine, iodine, halogens. Elements in a periodic table have similar electron configuration, valence shell electron configuration. Elements in the same group have the same number of valence shell electrons. They are similar, same number of electrons. Group 1A, these are called letters with 1A to 8A are called main group elements. Then 1A number 1A has 1 electron, 2A has 2, 3A has 3, 8A is the noble gas. There's an exception. Helium will have only 2 valence electrons out of all these noble gases. Chemical properties of group are very similar because of each element in a group has the same number of valence electrons. Valence electrons, outermost electrons, are the ones that participate in bonding. Chemicals react, elements react with their electrons in the valence shell to form bonds with other elements. Now I'm summarizing it. Group 1A, that's lithium, hydrogen, lithium, sodium, potassium. Hydrogen has 1s1, 1 electron in the 1A is the same as 1 is same as group number 1A. Lithium also has a 1 valence electron. Second group has 2 valence electrons. Second shell is the valence electron for beryllium. Third group, main group, valence shell is 3 valence electron. Carbon is 4. Nitrogen is 5. Same as valence shell group number. 6. 7. This is 7. 8, except helium. All noble gases except helium has 8 valence electrons. Helium is the exception. Now this is gone to all other next member of the group. They have same number of valence electrons in the group. We're going to answer a few questions. Which of the following is the correct Lewis dot structure of the nitrogen atom? Nitrogen has Lewis dot structure is a valence shell distribution in the electron distribution in the valence shell, Lewis dot symbol. This is nitrogen. Nitrogen has 5 valence shells, valence electron. They normally, there are, we said p orbitals, because of p orbitals distributed over the each one. This is the correct answer. You can tie this up, going back and looking at electronic configuration. This is S2, P3. How you get P3? That's S filled up. You put 1 in each. There are 3 unpaired electrons. D is the correct answer. Oxygen atom. Oxygen has 2 unpaired electrons. That one. Answer is A. Which of the following determine the number of valence electrons in a main group element? Main group is groups with 1A through 8A. There are 8 of them. That's the element's column number. Column number, that one. Answer is C. Which statement is true of the electronic configuration of a family in the periodic table? Family is same as group. They have same electronic configuration, valence electronic configuration. Not equal, not true. The group has same, that's true. Valence electrons are always paired, no, sometimes unpaired electrons. Valence electron never paired, that's not true. B is the only correct answer. Now we're going to look at properties of elements. In the periodic table, we classify the elements. We talked about their names coming from symbols coming from atomic symbols coming from names. We also look at periodic electronic configuration. Now, beside that, there are certain physical chemical properties, especially chemical properties in the periodic table. Sometimes physical size of the atom. With an understanding of electronic configuration, we can explain the periodicities of chemical properties in terms of electron configuration. Periodic table work because elements in the same column or group have the same outer shells as valence shells. We look at 2 periodic properties, atomic size and ionization energy. Size is how big an atom is. These are 2 atoms, this is smaller, this is bigger. Ionization energy is from an atom to pull out an electron. Energy required to pull out an electron and make a, for example, if sodium, take sodium and remove an electron, sodium ions are formed, an electron. That's the ionization. Ionization is removing 1 electron or more electron. That's energy is also dependent on the chemical reactivity. If low ionization energies, it's easy to pull out electrons from metals, therefore they are reactive. So there are trends in atomic size and ionization energy in periodic table. Trend means certain way going across down the group, how these properties vary. Atomic size. Atomic radius is, atom is determined by the radius of its outermost occupied orbitals. The last shell, atomic orbitals, decide the size of the valence shell. Atomic orbital decide the radius of a shell. For example, if a radius, electrons are in 2s level, 2s1, and another element is in 2s2, 4s2, that's a bigger atom. 4s2 is radius of the outermost shell is the highest number shell. Radius of chlorine is determined by size of the valence shell is 3s2, 3p5. Is determined by the chlorine as this. If you look at the carbon, carbon is a smaller atom. This is 3s2, 3p5. This is 2s2, 2p, 2p2, 2p2. This is smaller. Can you see carbon is smaller where the valence shell is second shell, this is the third shell. As the shell number increase, atomic size increase. So when you look at the carbon, there are two more, that's chlorine, that's oxygen, carbon 2, C2. Atomic radii in the main group, there's 8 of them. They didn't show the noble gas, it's 8A. We didn't show their gases. We don't talk about that. In going across the periodic table, in a period of, in the periodic table, atomic size decrease, becomes smaller. Group, atomic size increase, become larger. Going across, decrease also. Left bottom to right up. So you can, for example, if I ask you which one is bigger, carbon or nitrogen? Carbon is bigger, 77, 75. So periodic table could be used to roughly get the idea of the size of an atom, atomic radius. Which type of subatomic particle does the atom gain or lose, become an ion? Which type of subatomic particle does an atom gain or lose to become ion? Atom become a cation by gaining electron. Atom gain electron, become anion. Atom loses electron, become a cation. Cation and anions are ions. It's the electron loss or gain. And atoms gain or lose electrons. Neutrons is wrong. Protons is wrong. It depends on the atom involved. No, regardless of the atom, gain or lose electrons. Therefore, answer is C. Which of the following statements have the largest atom? What elements have the largest atom? How do you go do about it? Going across. Decrease. This way. Increase. So aluminum and magnesium. Aluminum is here. Magnesium is here. Same group, period. Therefore, aluminum is bigger. Sodium is here. Lithium, beryllium, sodium is here. You have to look at the periodic table. Aluminum, let's look at the periodic table. Aluminum, magnesium, and sodium. Look at this picture. Magnesium, aluminum is bigger. And sodium is bigger. You see, they are asking sodium, magnesium, going across the period, it decreases. Therefore, sodium is the biggest. Smallest atom, aluminum, going across the period, sodium, magnesium, aluminum. Which of the following has the largest element? This going down a group, sodium, potassium, rubidium. So has the largest atom is rubidium. They are asking is what is the smallest atom is sodium. Which of the following is the largest atom? Potassium. Which of the following is the smallest atom? You go through the periodic table and have the smallest atom. Smallest atom is which of the following has the largest atom? You have to go to the periodic table. If you have to find out where the elements are. So from my experience, largest is this is group shell number 3. This is shell number 3. This is shell number 3. Oh, shell number 3. Therefore, sulfur has the, chlorine has the, phosphorus has the largest element. Let me go back and look at it. Chlorine is 2, not chlorine. Phosphorus is the right here. It is little bigger. Therefore, phosphorus is the answer. Rest of are in the second period. The largest atom is phosphorus. If I had a periodic table right here, I could have done it. When you take out that, smallest atom is chlorine. Let's finish this. Ionization energy required to remove electron from an atom. Ionization energy decrease, reactivity increase. Ionization energy increase, going across the period. Going down a group, it decreases. So this is going across the period, increases. Going down a group, if the atom become bigger, ionization energy decreases, more reactive. What is the ionization energy of an atom? Energy required to remove an electron from an atom. Which of the following is true when comparing two electrons that are in different shell of the same atom? Electron in a higher number shell is closer to the nucleus and easier to remove. No, that's not true. It's not closer. The electron of the higher number shell is closer to the nucleus and it's hard to remove. High number. This is true. I'm sorry. This is the wrong one. It's easy to remove high number shell. Electron in higher number shell is further away from the nucleus and it's easy. This is wrong. It's not closer. High number shell. This is correct. Electron in a higher number shell is further away from the nucleus and is harder to remove. It's easier to remove. Only correct answer is C. When a potassium loses an electron from which is potassium last valence shell is in 4s1. D is the answer. Now I finished going over the material. Are you guys there still? Can you sign up the chat box? Can you guys hear me? I'm going to
Yes,
put,
we can.
I can hear you.
okay, I'm going to put the material in the Canvas web page. You can go back and look at again very carefully. All right. I will see you on next Tuesday. We're going to review the material. All right. Take care, everybody. All right.
Bye bye.
Bye.